Hi, my name is Dr. Ahmath. In this video, we are going to discuss about defluorescence quickly. So it's always interesting to understand the interaction of the light with the matter. So the light can go through the matter or it can bounce out or scatters out from the matter. So there is a certain type of the molecules which can absorb the light and then re-emit that light. So this type of the molecules are going to be called the fluorophores, and this process of absorption and then re-emission is going to be called as the fluorescence. So it appears the fluorophores are sensitive to the wavelengths of the light. So essentially, they can absorb only a certain wavelengths of the light, and also they can re-emit a certain wavelengths of the light. So let's look inside the fluorophores, especially to the energy levels, to try to understand what is this wavelengths is and how we can define those wavelengths to be absorbed and emitted. So here I drew the energy levels of the molecules. So that first the ground energy level, the first energy level, excited energy level, and the second excited energy level, and so on. So as actually all of these energy levels are associated with a certain type of the energy. Unlike for the electrons, for the molecules, we're going to have a vibrational states there in between of those electronic states or of those energy states as well. So this means essentially the molecules can lose the energy through the vibrations or the rotations. So now what happens is that whenever a molecule gets gets an energy, gets a light, whose wavelengths or the energy associated with that light is bigger than the difference between the ground state and the first energy level or the ground state and the second energy level, then this molecule is going to be excited. So it's going to go up. So it may go through the vibrational states to the first excited state, which is going to be a semi-stable, and then it may fall down suddenly to the ground state. And whenever it falls down, it's going to emit the light. So this process is going to be called as the fluorescence. So again, so I'm going to draw it here. So you see, so this light may have 450 nanometers wavelengths, okay? And the light which is emitted is going to maybe have 600 nanometer wavelength. So, and if you remember, as the wavelength is longer, it is going to have the smaller energy. So this photon or this light is associated with the smaller type of the energy. So this is, well, the first scenario, what may happen. So there are different scenarios what may happen whenever the molecule is excited. So let's look to them as well. So it is possible that the molecule is going to be excited to the first energy level, then it may go through, above the first energy level, then it may go to the first energy level, then it may go down to the ground state through the vibrational states. So this transition from the first energy level to the vibrational state is going to be called as the internal conversion. So you see, so in this case, there is no photon is emitted. So that is why this type of the relaxation, so whenever the molecule is going to be excited by absorbing the light, but it's going to be relaxed without emitting the light, is going to be called as the non-radiative relaxation. So the internal conversion is one of the ways of non-radiative relaxation of molecule. So there is another scenario where the molecule is going to be excited until some point, and then it may go through the first excited state. Then instead of just falling down to the ground state, it may go to so-called triplet state. So and then fall down to the ground state from the triplet state and emit the photon. So this process, when the molecule is going to be excited and then emit a photon, not through just by going through from the first excited state, but it's going to go to the ground state from the triplet state, is going to be called as the phosphorescence. So I'm going to briefly explain you what does it mean, this triplet state, and how it is associated with the the first excited state. So essentially, all the pairs of an electrons on the ground state should have an opposite spin. So essentially, this two, if you would just assume that you've got two electrons here, so they should have an opposite spin. So whenever the molecule is excited, so essentially one of the electrons is going up to the first excited state. So that is why it can't just stay for a long time on the first excited state. So it will just fall down to the ground state to its pair. So it may happen suddenly that the spin of that green electron may change. Okay, so then the spin is going to be, so the spin of the pair of electrons are going to have the same direction, right? So this blue one and the green one are going to have the same direction. So this state, when the pair of electrons are going to have the same direction, spin direction, is going to be called as a triplet state. So this triplet state is associated with a smaller energy than the first excited state. Then okay, so this is this scenario number 3, which essentially, if you have been asked whether which process is faster, the fluorescence or the phosphorescence, the obvious answer would be the fluorescence is the faster one, since the phosphorescence is so the molecule or the electrons are going to go to the triplet state and then come back to the ground state. So it's going to be longer than the fluorescence. And the last and this intersection. So whenever we're going to change, whenever the molecule is going to cross from the first excited state to the triplet state, is going to be called as the intersystem crossing. Okay, so it is abbreviated sometimes as the ISC, intersystem crossing. So it is also possible that the molecule is going to be excited until some level, then it's going to be relaxed, and then it may go to the triplet state, and instead of just falling down to the ground state, it may suddenly go back to the first excited state. So again, so if you or remember, we talk about the spins, right? So the direction of the pair of electron spins are going to define the singlet state or the triplet state. So again, if the electron spin is changed suddenly, it may go back to the first excited state, and then falling down to the ground state is going to emit the photon. So here are essentially the 4 scenarios which of the interaction of the fluorophores with the light. Okay, so this process, when the light is emitted, right, from the fluorophore, but we have lost some time to go to the triplet state and coming back from the triplet state. So this process is going to be called as a delayed fluorescence. And again, so in the 3 type of the scenarios, which we've considered 3 out of 4, we are going to observe the fluorescent signal. So the light is going to be emitted, right? In the case of the fluorescence, or in the case of the phosphorescence, or in the case of the delayed fluorescence, we're going to receive the fluorescent signal. So this is essentially what is going on inside the electronic energy states of the molecules, and this explains us what energy, what light is going to able to excite the molecules, and what light we are going to observe, right? Good. So now the next thing which I would like to talk with you is the excitation and emission spectra. So essentially, a specific fluorophores can be excited at the specific wavelengths of the light. For example, in this example, we are looking for the YFP fluorophore. So this is the name of the fluorophore. So this can be excited. This fluorophore can be excited with the light with the wavelengths roughly between 450 and 550 nanometers. And the height of this curve here means the intensity. So essentially, if you've got a sample of lots of fluorophores, okay, and if you are emitting this sample, if you're just flashing this sample with the light with the intensity 515, then all of the fluorophores in your sample are going to be excited. Okay, so if you are going to flash a light at this wavelength, so let's say it's going to be 475 nanometer, roughly 40% of the fluorophores in your sample are going to be excited. So again, so the width or this direction is going to be mean the wavelengths of the light, which can excite the molecules, the fluorophores, and the height of this curve is going to be mean the intensity. So again, we are going to have a similar curve for the emission spectrum. So essentially here, this curve means at which wavelengths the light is going to be emitted. Okay, so you see, so there is a difference between the emission spectrum and the excitation spectrum. So this dashed line is going to be called as the excitation spectrum, and the green line, so which is like felt was the color, is going to be called as the emission spectrum, right? And you see that there is a shift between the excitation spectrum and the emission spectrum. The shift is going to be called as the Stokes shift, right? So you see, so the excitation, so if I would just denote the lambda 1, the wavelengths which can excite the fluorophore, and the lambda 2, the wavelengths of a light which has been emitted. Which lambda is going to be longer? So the lambda 1 or lambda 2? So obviously from this graph, I can see that the lambda 2 is going to be longer. And if you remember, the wavelength is inversely proportional to the energy, right? And it means that the energy or the frequency which is associated with the first lambda is going to be bigger than the frequency which is associated with the second one, right? And we can explain this using the diagrams which we have seen before. So if you remember, the molecule has been excited until a certain level, then through this vibrational states, it falls down to the first excited state, right? So there was a loss of energy in the vibrational states, right, in non-radiational fashion. So that is why there is an energy difference between the excitation and the emission ranges. So this is called the Stokes shift, and this is due to the loss of the energy in the vibrational states. Okay, so there are a couple of properties of the fluorescence which we need to discuss. So one of them is going to be called the quantum yield. It's a ratio between the number of the photons absorbed and emitted. So essentially, intensity of the signal which we are going to get can be quantified using the quantum yield. So essentially, so if you've got some fluorophore, now let's assume that you can count the number of the photons which can be absorbed by this fluorophore. So let's say 3 photons are going to be absorbed by this fluorophore, and 3 photons are going to be emitted by this fluorophore. So in this case, we say that the quantum yield is equal to the 1. So since 3 out of 3 have been emitted. But what happens if 4 photons have been absorbed, and only 3 have been emitted? In this case, the quantum yield is going to be equal to the 0.75 or 3 over 4. So essentially, this quantum yield represents how good the fluorophore to emit the signal, right? And of course, it depends on the excitation range. Of course, it depends on the light source, and so on. So another parameter which defines the fluorophores or which makes the two fluorophores different from each other is going to be called the fluorescence lifetime. So essentially, we are going to measure the fluorescence lifetime using, again, the exponential curve. And I'm going to explain you this in a moment. So let's say I've got a sample here where with lots of fluorophores there inside. Okay, so let's say this is the YFP fluorophores. And if you remember, if I would just flash a light at the 515 nanometers wavelengths, so it can excite all of them, right? Okay, so let's assume that I've been able to excite all of them. Now I will just switch off the light, the source, And I will see how the excitation, so all of this fluorophores are going to be relaxed. Okay, and then I'm going to just track the number of the excited fluorophores over the time. Well, at the time is equal to the 0 here, so the number of the excited fluorophores is going to be 100% or equal to the 1. Okay, so as time is going on, as time is going on, the number of the excited fluorophores is going to be decreased, right? So they're going to be relaxed. So we call the fluorescence lifetime. So let's assume that after a certain time, for example, after 1 second, for example, the number of the excited fluorophores is 50%, right? If you used to have like 6 fluorophores which were excited, so now we have only 3 of them which are excited. Only 3 of them are excited. Okay? Then later on, I'm going to just like track this process, and whenever I've got only 37, roughly 37% of the excited fluorophores, I will just keep this time or like a fix this time, and this time is going to be called as the fluorescence lifetime. Okay, so you can just imagine this fluorescence lifetime as we've been able to excite a molecule, right? And this time between the molecule has been excited and fall down, relax, is going to be a fluorescence lifetime. And mathematically, we're going to quantify this in this way. So essentially, this is the fluorescence lifetime is going to be defined as the time which takes until the intensity of the sample with the fluorophores is going to be decreased until 37% of the initial one. Okay, so this is essentially what is the fluorescence lifetime. So there is a couple of applications of the fluorescence, and one of the fascinating applications of the fluorescence would be something which is called like a fluorescence resonance energy transfer, or we call this as a FRET. FRET. So the essential idea is like this. So let's assume that I've got 2 fluorophores, okay, and I'm going to try to excite the first fluorophore. Okay, so I'm going to excite this using the light in the excitation range of the first fluorophore. And now the first fluorophore, instead of emitting light, it's going to transfer this energy, which has been absorbed, into another fluorophore, to the second fluorophore. And the second fluorophore is going to fluoresce. It's going to emit light. So this energy transfer between the first fluorophore into the second is going to be called as a FRET. Fluorescence resonance energy transfer. So I'm going to call the first fluorescent as a donor, and the second fluorophore is going to be called as an acceptor. Acceptor. Okay. So again, so there are a couple of factors which affect to the strength of the FRET signal or to the strength of this process. And one of the the 3 important factors which will affect to the FRET is the R, the distance between the donor and acceptor. So if they're close enough, then we're going to see this emission of the light from the acceptor. If they are far away, then I'm going to see the emitted light from the donor and not see the light from the acceptor, because this energy is not going to be transmitted to the acceptor. So overlapping spectra, so it actually means that the light, yeah, so the acceptor is going to be excited at a certain range, right? And if this certain range is going to overlap with the emission range of the donor, then the acceptor is going to be able to get that energy. And the last one is essentially means the proper orientation. It is a little bit difficult to explain, but you just need to understand that, hey, if you've got just like a 2 fluorophores, they need to be some in a proper orientation so that they can just fit to each other. Okay, so they can come closer to each other. So now let's talk about in each of these factors in a little bit in more detail. So emission and absorption spectrum of the donor and acceptor pair must overlap. What does it mean? So we've discussed that, hey, so every fluorophore has its own excitation range spectra and the emission spectra, right? So let's say here I drew the blue with the blue light, the excitation and absorption, excitation and emission ranges of the donor, and the red line is going to represent the excitation and emission spectra of an acceptor. So you see, so the acceptor is going to be excited only in this range, right? So only in this range. If the donor is going to emit the light in this range, which is going to overlap with the excitation range of an acceptor, then the thread is going on, right? So the energy is going to be transmitted to the acceptor. So as this area overlapping of the emission spectrum of a donor and excitation spectrum of an acceptor is bigger, then the strength of the thread is going to be more. Okay, so actually, what is the strength of the thread? So we are going to define the strength of the thread as the ratio of the number of the donors which has been transmitted the energy to the acceptor from overall number of the donors. Okay, so if all of the donors have been transmitted the energy, then efficiency is going to be equal to 1. If no of the donors have been transmitted the energy to the acceptor, then the efficiency is going to be equal to 0. Okay, so efficiency again depends on this area of the overlapping the spectrum, and the second factor which affects to the efficiency is the distance between the donor and acceptor. And it appears we can even see the exact relationship between the distance and the efficiency using this equation. So here in this equation, there are lots of letters. Let me explain you all of them one by one. So again, so here this R naught in the power of 6 is a constant which is going to depend on the pair of the fluorophores. So this constant R naught is measured. So, and it represents the distance at which the efficiency is going to drop to the 50%. So let me explain you one more time what does it mean. So let's say you've got 2 fluorophores. If they are close enough, then so the thread is going on. So essentially the energy from the first fluorophore is going to be transmitted to the second. Okay. In your sample, all of the donors are going to transmit the energy to the sample, to the acceptor. So that is why the efficiency is equal to the 1. So as you are going to make apart them, so if the distance between them is increased, then obviously the number of the donors which have been transmitted to the energy to the acceptor is going to decrease. Okay, so what I'm going to do is I would like to measure this. For example, what is the distance? Maybe the distance is 1 nanometer, 2 nanometers, 3 nanometers. Okay, then I fix the distance. For example, at this point, 3 nanometer. Okay, when only the half of the donors are being transmit the energy to the acceptor. Okay, so let's assume that in your sample you've got 100 fluorophores, 100 donors, and 50 of them are being transmit the energy to the acceptor. So this is essentially is associated with the efficiency of the thread, which is going to be equal to the 50% at this distance. Okay, so I'm going to just fix this for a specific pair of the fluorophores. Okay, and now what I would like to do is I would like to theoretically calculate the efficiency depending on the distance. So now I know that exactly at the 3 nanometers, the efficiency of the thread between these two specific fluorophores is equal to the 3 nanometer. At the 3 nanometer, the efficiency is equal to the 50%, sorry. So I would like to know if the distance is equal to the 5 nanometers, what is going to be the efficiency? So in order to do this, I just need to plug in everything to this equation. So essentially here, I need to plug in 5 nanometers, right? So instead of R0 in the power of 6, I need to plug in 3 nanometers and calculate the efficiency, okay? And you can see in this curve, it is basically going to explain us how the distance is going to change, how the efficiency is going to change over the distance. So usually the thread is going on between 1 and 10 nanometers. But again, you see, so the efficiency is going to drop down after this R naught. So essentially, if the R naught for the two pair, so for a pair of fluorophores is equal to the 3 nanometers, so after you are going to split them more than 3 nanometers, so the efficiency is going to drop down rapidly. So this is about the two things which will affect the thread. So essentially, the overlapping, the region, the distance, which was also distance also will affect to the efficiency of the thread. So now let's talk. So here are the table of the commonly used thread pairs, and there are not. Then again, so it's better when you have this R naught with a bigger number. For example, if you see here this two pair of fluorophores, so the citron and strawberry, so they are not as equal to the 6.24. So what does it mean? So essentially, when they are really close to each other, where the distance between them is equal to the 0, then the efficiency of the thread is equal to the 100%. So in your sample, all of your donors are going to transmit the energy to the acceptor. And as you increase the distance between them until 6.24 nanometers, 50 of the donors, so 50% of the donors are going to transmit the energy to the acceptor. So this is actually a huge distance, a relatively big distance here, was compared to the other pair of the fluorophores. So as this distance R naught is bigger and bigger, this is better for us because it helps us to understand the interaction between the other substances. So one of the applications of the thread has been used in the medicine and is to understand the interaction between the molecules. Before we discuss this, let's discuss something which is called a photobleaching. So it's a process when the molecule, the fluorophore, is going to lose its ability to fluoresce. So essentially, if you've got a fluorophore, so if you just excite this fluorophore using a light from the excitation range, it's going to emit some light. We can see this light. So what happens if we just flash the fluorophore with a really intensive laser beam for a small period of time, so for some period of time. So after some period of time, it appears, so the fluorophore is going to lose its ability to fluoresce. So this process of losing the ability to fluoresce is going to be called the photobleaching. So now let's talk about the applications of the thread, especially. So I would like to understand the interaction between the two proteins, for example. So I'm going to stain a certain type of the fluorophores with those proteins, okay? And for example, with the CFP, let's say, so I've got the CFP, which can be excited at the 430 nanometer wavelength, and it's going to emit the light at the 490 nanometers. So I've got another fluorophore, YFP, which can be excited at the 490 nanometer and can emit the light at so probably it's 520 nanometers. Okay, so you see, so the emission spectrum of a donor is going to be the same as the excitation spectrum of an acceptor in this case. So what happens when these two proteins, which are stained with the fluorophores, come together is that instead of getting a signal from the donor, I will get a signal from an acceptor. So essentially, the wave, the light which we're obtaining is going to be at the 520 nanometers. It means that those molecules are interacting. So this is one of the applications of the thread, but there are many more applications of the thread. So it helps us to understand the interaction between the molecules. And this video was about the quick review on the fluorescence. Hopefully that was helpful. Thank you very much for your attention.